is my official recording. So back on air here. So I'm talking about the chain rule and a little limited show you how it's used in physics as well as in math. But we need it on 411 and we need it on the number 13 on the take-home test, 4B. So it's used like we have, trust me, I mean, I'd rather just not do it, not introduce it. But when you do sines and cosines of time-related functions, you have to use the chain rule. So chain rule are for functions that are nested inside of the functions. A function of a function. Remember this from math class where you have f of g of x. Now, if I want to take the prime of that, or in math class you call it prime, which means the derivative, I have to do it for the whole thing. Then I have to go inside the nest and do it for the things in the nest. So when you have, and if I say, now if in math class I say something like sine x, well, x is not a suitcase. Suitcases are formulas that have other variables inside them. Like essentially, I mean, to be honest with you, velocity is a suitcase. V is dx dt, and so inside the velocity there's an x and there's time, et cetera, et cetera. So these are symbols which represent fundamental variables put together in different ways. Force, energy, work, all of those, kinetic energy, all those are suitcases we use. So when you take a derivative of one of those suitcases, and really, I mean, sine in physics, sine of omega t, that's a suitcase because it's not sine of x, x equals omega t. So you have to, so when you take a derivative, how that thing is changing, you have to look at the whole thing changing and then the pieces changing. Okay. So that's an overview of when you use the chain rule, which by the way is a lot. So let's take, for instance, let's do a contrived example here. And here's the general, so write this down, and it helps if you have a colored pencil or something, but write this down. This is the general chain rule, the Leibniz notation of the chain rule. You put a box. If I have something, some derivative related to something, that's going to equal, I'm going to split that up. Now, I didn't originally learn it this way. I didn't learn it this way until I started getting more into physics, and then it made more sense. Math is just a series of rules, and a lot of times you don't know why you're doing it. So now I'm going to color in this box. And we're going to go yellow, yellow, and we're going to go green. I'll go purple, 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 and then I'm going to go green, green. This is the general Leibniz setup for a chain rule situation. All right, so keep that in mind. I'll give you a second to color that in. Hopefully you have color pens or crayons or something. Okay, now let's look at a situation. Let's say, this is our situation. Let's say that we have ants, let's say there's 100 ants, and they are on a driveway, and there's some sugar water, and so those 100 ants are all around, here they are, 100 ants, they're all around the sugar water getting a drink. And then you come along and go boo, and so they all take off running. Let's say that the ants run at, let's beat this up to let's say 5 centimeters a second. Say that's the ant, each ant's speed. Let's say they're good grief, let's say they're all running at the same speed. Notice I didn't say velocity because they're in different directions. They're running radially. Now, this is a dumb little example with ants, but it has implications of explosions, right? An explosion, the particles come out radially. Any electromagnetic wave emanates radially. Stars shine radially. So, it's pretty common. This is two-dimensional. Three-dimensional is a little bit, we can do it, and we do it in AP Physics, but we're not going to worry about three-dimensional stuff today. We're getting the basic idea of chain rule, okay? All right, so far so good. 14 people, all right. So here's the question. If this is what's happening, you see all the ants, they're all running away from the sugar water, all radially out. And the question is, I know how fast each ant is running, but the question is, how fast is that circumference of the circle getting bigger? That's what I want to know. How fast is the circumference growing? Not how fast is each individual ant running. So that's what I mean by nested functions. The ants are all part of the function of the circumference. They're a part of it, but I want to step back and look at the big picture. Let's see how the circumference is growing. Okay. So we're going to plug it into our equation back here. I mean, our little colored boxes here. So what I want to know is, I want to know the change in circumference with respect to time. But when I look up the equation for circumference, I get 2 pi r, right? Anybody in calculus would never say pi d. I mean, you might say that in geometry, but in calculus, you would never say pi d. There's a reason for that. Side note. Anybody know the reason for that? Why you would never call it pi d in calculus? Side note, area, the equation for the area of a circle is pi r squared, right? Pi r squared. When you take the derivative of the area of a circle, let me pull this up, sorry. When I take the derivative of the area of a circle with respect to r, see, that's why this is where Newton's notation wouldn't work. Like I can't say area dot because to say dot, like x dot, v dot, a dot, it has to be in relationship to time, but a lot of times it's not. So this is a perfect example. But if I take the derivative of area with respect to time, or sorry, with respect to radius, I bring the 2 down, right? And then you subtract 1, and that's 2 pi r. So that's true. The area, if I have the area of a circle, I want to know what the perimeter is, I take the derivative, okay? It's kind of cool. If I want the volume, say I have the volume, all right? Well, let's do one more, let's just for fun. If I have volume, well, let's do a sphere. Volume for a sphere, one thing you should know for the ACT exam, 4/3 pi r cubed, right? That's the volume for a sphere. But the surface area, to find the surface area of a basketball, I know the volume of the basketball. The surface area is the derivative of volume with respect to radius. So I do that again, I get 4 pi r squared, which is the formula for the surface area of a sphere. So it just shows where a lot of these formulas come from. They come from calculus. Those are all side notes. Since I'm not going to get much of a chance to talk about that the rest of the year. So back to our thing. So if I want to find, the thing is, if I want to find the derivative of the circumference, like if I take the, if I want to know the derivative of the circumference, which I know is 2 pi r, with respect to t, what? You can't do it. There's no time. There's no time in this formula. So you throw up your hands. I don't know what to do. What you do is you employ the chain rule. Say, okay, now wait a minute. I know that circumference is changing. And I can take this. What I can do is I can break that Leibniz notation up. And that's why this is also a yellow box. That's DC. I move the DT there. And I'm going to bring something in that's legal. It's legal to multiply by 1. A green box over a green box is 1. So I'm not breaking any rules from algebra. And what I'm going to bring in is dr. dr. Now, this is this dCdr, I've already done that. I did that up here. DC, well, I haven't done it yet, I guess. I did dAdr and dVdr, but I could do dCdr too. This is simply the derivative of 2 pi r with respect to r. Okay? And that is simply, that is simply 2 pi, right? Because the r is to the first power, you bring it down, and okay. Now dr dt, what the heck is that? Well, that's simply the velocity, because it's the changing radius with time. That's simply the velocity of the ants. That's the velocity of the ants, of a particular ant. They're all going the same. I better be careful here. I'm going to call it speed, because they're all going in different directions. So it's speed of a particular ant. Okay. So that is simply V. Well, I'll call it V, and giving a particular ant, I can say V. But we know, we already talked about that, and that is, from this right here, we said it's 5 centimeters per second. So I'm just going to call it right in there 5 centimeters per second. And so my answer is the rate at which the circumference is changing, dc dt, is 2 pi times 5 centimeters per second, or 10 pi centimeters per second. So about 30, which same thing as 31.4 centimeters per second. That's how fast the circumference is growing of that circle, which is kind of cool. I mean, I could see it using it like in astrophysics or something. If a star is exploding and you want to know, well, how fast is that circumference growing? When is it going to overtake this planet? So you can beef this up to a 3-dimensional object as well. All right, so it has a lot of implications. And of course, explosions. How fast is that concussion wave going to grow out, and what is going to be the circumference of that concussion wave? Say it's in downtown Nashville, like that explosion was. Well, they'll go back and reverse engineer it, and then determine, how much plastique or whatever they used from doing the physics, how fast that thing, looking at footage or whatever, how fast that thing grew. Okay, so that's one practical example of the, I went back and got these from AP Physics from like 6 or 7 years ago. Another one is the same idea now. If I have, let's say I have a piston in a car engine. Okay, and so we have the chamber, and then I have a piston here, and it is moving up in the chamber, let's say. So we got a piston, well, it's actually moved down. Oops. Oh, well, I'll make this one move up. So we got a piston moving up in the chamber. And my question is, I want to know, how is the volume say the volume of remaining space. Okay, you have your intake valve and the X valve. The volume of the remaining space. No, that's right. The pistons go this way. We're good. Sorry. But how is that changing with time? In other words, what is d volume dt? How is my volume of what's the space left as that compresses? How's the volume changing with time? So I set up my system, my Leibniz system here, my boxes, and I make the AP kids kind of do this, at least for a little while, so they get the hang of it. Okay, so we have our colored boxes, and now you think about this. What we're trying to solve for, I'm getting to cosines and sines here in a second. Okay, that goes there. That goes here and here. And then my green is what I'm going to bring in to get inside that. Okay, so I want to know what is the change in volume. I'll just say VOL so you don't think it's velocity. What's the change in volume with respect to time? How fast is that volume dropping? Okay, so I'll put D volume here and I'll put DT here. Now the question is, what do I bring in to make this work? Well, we have some length here. There's a length of that tube. And so I can determine how fast that piston is moving up. I can do that. And so that would be DL dt. So if I bring in the change in length, DL dl, I can then do it. I can then solve for how the volume is changing of that chamber with time. So volume for a cylinder is the formula for volume of a cylinder. Maybe remember this from geometry, is pi r squared times L, right? It's the circle times how far up it's going. It's a volume situation. So I can find that, and let's say that it's moving, and these pistons move really fast. Carlos could, I don't know if Carlos is here, but he could cue me in as to how fast he works on cars all the time, how fast that piston's moving. Let's say it's moving at 100 meters a second. Say 100 meters per second is my dl dt, how fast that piston is moving up in the chamber. So we say, okay, I want to know how fast is the volume, how fast is my volume changing of my chamber? How fast am I losing volume? Well, I go and take the derivative of volume with respect to L, and that's just pi r squared, because I take this, the L goes away, right? And then the dl dt now is 100 meters per second. So now I have 100 pi r squared meters per second is how fast, and make it negative, I guess, if it's getting smaller. So that's how fast my volume is changing. Okay. Another example of needing chain rule to work mechanical engineering, to be a mechanical engineer. Okay, so you kind of have to know chain rule. Now let's go to more of a standard calculus math problem. If I have a situation like this, and this is a suitcase, okay, let's say I have a suitcase. I have a suitcase problem where I'm trying to find dz, some function z, dt. Well, dz dx I can do. That's going to be dz dx and then dx dt, because x is a function of z, z is a function of x, but x is a function of t. So that's what I mean by it's a nested. This is nested inside the suitcase. And the more you get into physics, the more suitcases you encounter, meaning that this symbol means they get tired of writing it every time. So they just show, okay, this means, they're always using operators and symbols. And so that their goal is to be able to put an equation on a t-shirt. And so you see these, all these functions, but it means but that's really a suitcase. It really means a bunch of other things. They just get tired of writing it every time. So let's say we have, instead, so that the person gets tired of writing 6t to the fourth plus 2t plus 4. And so they just say, I'm going to call that x, okay, because I'm manipulating that guy. And so if we're going to find the chain rule, then what we do is to find dz dt, I go ahead and take dz dx, which is 3. If I would say 3x, well, x is 6t to the fourth plus 2t plus 4, and then squared, right? Because I bring the 3 down, I take away 1 from the exponent. Then that's dz dx. Then I got to go inside the nest and mess with that, and that's dx dt. So dx dt, then I go inside and say, okay, that's 24t cubed plus 2. So I went inside, and let me highlight these so that color code them together. So that's this part, and that is this part. So you see, you had to open up the suitcase and go inside it and pull out how it's changing. Okay. So that's the idea of nested functions and chain rule applying to them. Now, let's just keep going. Let's keep going. Because I want to get to the, okay, so now I want to get to our situation, and let's go back. So in our situation, we have, like, if I have, say I have cosine, say that x of t, preparing, what's it, cancel. It just has a mind of its own. Why would it want to, spending all this money? It's not helping. X of t equals, let's say, a cosine omega t, okay? Now, just in general, forget any particular problem we're working on, but in general, I need to take its derivative. So velocity of t is dx dt. But I've got to now, it's like this is really, it's not cosine of x. Like in calculus class, you say, okay, cosine x, what's the derivative? Well, the derivative is negative sine x. But x, that's great, and it's good to learn that, but cosine of x is not changing, it's x. It doesn't make any sense in physics anyway. Why would you say x? X is a length. You don't take cosine of a length. So anyway, but math is saying x as your generalized variable. I get it. But it doesn't really work in physics. In physics, we're in the real world. So in physics, cosines are a function of time. They change, they oscillate, right? Over time. So it's really a suitcase. So what we have to do is we have to first take the cosine of the whole thing, take the derivative of the whole thing, and I'll pull the a out because a is like the constant there. So we say it's kicking me out again. I don't understand. It keeps shutting me down. It's just frustrating. I wouldn't mind it if I wasn't paying so much money. Anyway, so the my own money, by the way. So that's negative a sine, okay, omega t, and that's me taking the derivative of the whole thing, treating it all as one, and then I got to go in, and now I'm buffering, and then I got to go in and take the derivative of what's inside the suitcase. What's inside the suitcase is omega t with respect to t, okay? So, so the derivative of omega t with respect to t is just omega. Okay, so then you put omega, then that's times omega. Now, so the way you write this is the velocity then, if x is cosine, the velocity would be negative omega a sine omega t. You bring the omega up front. And that's how you do, in general, that's how you do that's how the chain rule applies to sines. Now let's do it again, because let you do it now. Acceleration is the derivative of velocity. So we have to go in, do the whole thing first, then go in and get inside the suitcase. So you do it. You try it. And we found out yesterday that the derivative that as cosine changes, we'll come back and look at this again. We get, so in general, if I have sine of x, the derivative of that with respect to x is cosine of x. Okay, just cosine of it, not negative cosine of x, just cosine of x. All right. So therefore, to go in and get that suitcase, we got to now do the thing. Okay, I'm going to make a cosine. So negative omega a cosine omega t. And then I got to go in and get the omega, because I got to pull that out of the suitcase. So that's really another omega. So I bring that up front, omega squared. So that's the way acceleration looks.
Would it just be positive?
Sorry. Go ahead.
Would it just be positive omega squared a cosine, because you're taking the derivative of negative sine, and then it'd be negative cosine, and there's already a negative in front?
No, it's not negative cosine. The derivative of sine is just cosine.
All right.
The derivative of cosine is negative sine. The derivative, and I'll show it to you in a minute. The derivative of sine is just positive cosine. So that negative just kind of came down. It was already there, so I just brought it down. Yeah. And now let's look and see why that is. So that's chain rule. Now the question is, that's a lot to take the day before the test. I don't know. My wife, Jamie, she says that we're going to be in school tomorrow. I don't know. I'll use remote tomorrow while I have you here. So if we're in school tomorrow, then the test is on. And the due date is tonight for this take-home test. So go ahead and turn it in. What I'm saying is turn it in. You have unlimited turn-ins. But then you start losing points after the deadline. Right now, the deadline is midnight tonight. But if they cancel school, if they don't cancel school, if they go remote tomorrow, then you obviously can't turn it in to the box. So in that case, I'm just going to push the whole test. It's going to be the same test. I'm not going to change it, but I'm going to push it back to next week on a Thursday, Friday, because you have to have test, feast, and film has to go together, right? We have to celebrate. So we'll just start, say we don't go to school tomorrow, but we go to school Thursday, we'll just start packet 5 on Thursday rather than do Monday. So we'll just do 5, and then we'll just come back on Thursday, Friday next week and just take test chapter 4 test. So in that case, if that's the case, all these scenarios, if they would just let us know, that would help, but they won't. They wring their hands. Just make a decision, for God's sake. Anyway, so if I'll write it all down. I'll put them. So it doesn't hurt. The thing is, it doesn't hurt to turn in your take-home test tonight, and then you can always, if the deadline gets extended to next week, you can always just keep working on it and change and turn in a new one. You have unlimited turn-ins. So I'm just saying, now we just learned the chain rule, and now question 13 comes out of it. Well, here is 411. And so let's look at 411. We have done some of 411 in classes, various kinds. But we have people from different classes here. It's not just the virtual kids. So let's go back, and really what I'm concentrating on, that's homework, those two. And that's just, there's no derivatives going on there. And that's theta. So we're not going to worry about that one. What I'm concentrating on are these three. Let's look at these three. And then if you can do these three, how much time do I have? Okay, then we'll take our time on these three. And then you can do 13 on the test, on the take-home test. And that'll give you a chance to practice on your own. All right, so let's go ahead and do this one again. I know we did it yesterday. Let's do it again quickly. So this is the position. And so remember, if it's a pendulum going back and forth, we're just looking at the X version of that motion. And so it's going to go between our envelope there, which you don't need to draw your envelope if there's no damping, but it's between 2 meters and -2 meters. And it's cosine because it's a pendulum. You have to give it amplitude, or it's not going to do anything. Like I say, it's cosine world. And so it's going to end up back where it was. And then it looks like we found that the omega, it said, is 0.7 pi is omega, 0.75 inverse seconds. So therefore we said TP was 2.8, right? Because it's 2 pi over that. And so it ends up being 2.8. So this will be true all the way down, this 2.8 business. Feel free to stop me anytime. We did this yesterday. I'm just repeating this. But I love your questions, so fire away at will. So this is 2.8, 5.6, and that was 8.4. Okay, and so this is a cosine wave. Okay, so make that look relatively good. I always think flat, 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 point of inflection, flat, flat, flat. Boom. Okay, so that's my cosine function. And the equation is x of t. Blow this up a little bit. Equation is x of t equals a cosine. So a is 2 meters. I'm gonna be lazy. 2 meters cosine omega t, which is 0.7 pi t bracket meters. Okay, so that's my equation. Now let's get to the new stuff. The velocity, as I think we started plotting the velocity. Yeah, we did. At least in not every class did, but we did. But I'm going to repeat myself. We did this virtually yesterday. But for velocity, hold on. Where'd it go? Okay, so all I have for a pendulum here is my AirPods here, and so velocity is now it's going back and forth as a pendulum. So velocity is changing. It's 0 on the ends. It's going the fastest as it moves to equilibrium. Remember, equilibrium is the point at sometimes called ground state, but the lowest point. So if I take this, I talked about this morning, but I erased that tape. That was terrible. I got rid of that evidence. So if I take this, at one point I started weeping. No, I'm kidding. If I take this and look at the tangent lines, well, those are all flat, right? They're all flat on the ends. So I know, so I can go down and what you're plotting here are what you're plotting in the V versus T are the slopes of the tangents. And so I can plot that. It's 0 right there. It's 0 right there. It's zero, so I know I'm setting up my scaffolding. So anytime I reach a maximum, a negative, positive or negative maximum in the position, I know I have a 0 for slope, which means no velocity. I mean, and I loved calculus. I really did. I loved it in high school. I loved it in college. But it means something. It's not just kind of fun little puzzles. I always like puzzles. It actually has meaning. 0 on the velocity means that there's no velocity on the ends. And then we have these POIs, right? These points of inflection right here. That's a point of inflection right here. These points at which the slope is changing the most. And so if I do a tangent line there, I'm seeing how that's where that And that, okay, I'm going back and forth. That is where I just want to kiss it. That's where that, my pendulum, my bob, in this case, my AirPods are considered a bob. My bob is going the fastest, right? Point of inflection means fastest change with time. And so down here now, that's going to be, notice that that slope is negative. I apologize if we went over this yesterday. But notice that slope right here is negative. So it's going to be a negative. And then here it's a positive point of inflection. So it's maximum maximum velocity. Well, now what's shaping up obviously is my a sine wave, a negative sine wave, and that's what we said. We said that the derivative of cosine is negative sine, and boom, there it is. Boom, there it is. And then this is like that. Okay. Okay. Like that. Okay. So this is negative sine. But now let's go write the equation. All right, so the equation then is x dot, and I can say dot now because it is with respect to time, but it's x dot. I'm getting nervous on my time here. I got 10 minutes. X dot equals v, which equals the negative sign, but then it's a nested function. So I've got to pull out the what's inside that suitcase, which is 0.7 pi. So it's negative. The 2 comes down as well. Negative 2 times 0.7 pi times sine of 0.7 pi t bracket, lazy, bracket, meters per second. Boom. Parentheses, just to be careful. So 2 times 0.7 pi is 1.4 pi. So that means that this, now my maximum, the maximum values of, it tells you how fast your velocity can go. That's what it means by, maximum values. How fast can my velocity be? Well, it can be, according to this, it can be 1.4 pi is as high as it can get. So 1.4 pi, which has a number, right? That's 3 times 1.4, so I don't know, 6 or something, whatever that is. And then negative 1. It's okay to leave it in terms of pi. Negative 1.4 pi. Those are my extremes for velocity, okay? Now, let's do it again. Let's do acceleration. And I can finish this off real quick. Okay, so now we do acceleration. And acceleration, we can do the same thing with tangent. Right here, I'll change colors to green. So, let me find all the points at which the tangent line would be flat, okay? That's kind of your modus operandi here. That means 0 acceleration. Up here, 0 acceleration at that point. 0, okay? Get it? 0. Got my scaffolding built up. 0. Whoa. Yeah. Okay, 0. All right. And then I'll look for points of inflection. Notice that's a positive point of inflection, so I'm up here. And that's a negative point of inflection, so I'm down here. Okay. And then et cetera, et cetera. And now I have my wave kind of laid out. So now let's do it. Boom. You go, oh, well, see, it's negative cosine. Yeah, because it was negative sine. That's why. That's why it's negative cosine. If sine was positive, cosine would be positive. Okay. I mean, in calculus, when I learned it, they just said, oh, memorize this. What? Okay. All right, I memorize it. No idea. Well, that's part of the puzzle. But I had no idea it meant something. teach math all wrong in America. Okay. So now let's go ahead and find the equation now. So the equation, and applying the chain rule. So here we go. Now we have V dot, which is A. And now I'm going to bring down everything I have, plus I'm going to pull out that 0.7, plus I'm going to switch to cosine. So it ends up being A equals negative, that's the 1.4, negative 1.4 pi times 0.7 pi again, times cosine of 0.7 pi t bracket meters per second squared. It's a weird universe, isn't it? But it's all, this is the way it works. Spitting truth. So that's, I don't know what's 1 point, hold on. What's 1.4 times 0.7? 1.4 times 0.7 is 0.98. So 0.98. So over here, I'm going to be lazy and call it 1 if you don't mind. So that's pi squared, right? 0.98. All right. I'll leave it as 0.98. So 0.98 pi squared, negative 0.98 pi squared. That's my limits on acceleration, which is getting pretty high now. I mean, 3 squared is 9. We're above 9 meters per second. That's pretty big. That's in other words, it's a lot of acceleration. Okay, the last thing, why is that acceleration so high is the question. But that right there is a chain rule. That also answer now number 13 on the take-home test. You can now answer it the same way you did this one. But last thing before we go, why is that acceleration? Why did it get so daggone big? And here's the reason. Oh, maybe I have that. Hold on. I may have it already drawn up somewhere. No, I don't. Okay, all right, fair enough. I can get it. Okay, so why is it so big? Look, real quick. And this leads into packet 5, son. There is let's say that's my pendulum on the far extreme as it's ready to come. It's right here. It's ready to come back. Okay, it's way out here. Well, what's causing the pendulum to go back and forth? It's gravity, right? So gravity's causing the pendulum to go back and forth. And so the forces, gravity's looks like this, and that's the force due to gravity, a free body diagram. And this is tension. We'll get into the free body diagrams a lot, I promise you. Tension, and then this is the direction of motion, DOM. I'll make that green. That's not a force. That's the DOM. And this is some angle theta. Okay, so when the pendulum is far out, the amount of, okay, let's look at the other case. When it's at equilibrium, down here at equilibrium, at that point, the force, we have two extremes. The force is down, the force of gravity is down still, and these are congruent. And the tension's back up, and these are, whoops, not congruent. Okay, what am I doing? Oh yeah, the force of gravity is congruent. Tension's changing. Anyway, so the point is that, and then direction of motion is this way. Okay, here's the rule on forces. When the force is perpendicular to the direction of motion, it plays no role. When the force is, the only thing that causes speed up or slow down is the force being in the direction of motion. The more the force is in the direction of motion, the more it causes it to speed up or slow down. The more push it's giving it. And so here on the end, when it's in this situation right here, that's maximum force of gravity, the maximum push. So maximum push. And that is why maximum, even though it's not moving, the push itself is the maximum. Something is easier to understand is a spring. And if we were in my classroom, I'd do the spring, we'd play with it. But a spring, as I compress it the most, even though it's not that the object going back and forth on a spring, as that spring gets compressed, the object's not moving, but the push to make it go back to equilibrium, make it go back, is the greatest. At when it's or in its maximum stretch, the push to get back to equilibrium is the greatest. And so that's why acceleration gets so big uh, compared to position and velocity on simple harmonic motions. Okay. Woo. It's 1:59. How about that? Well, that all made sense. Yeah.
Mr. Askey, I have a question.
Yeah.
So for C and D,
Yeah.
like you have the negative 0.98 pi squared and the negative 1.4 pi. How
Yeah.
did you get that?
I got that from, well, okay. Good question. Look at this. What's the biggest, what is the biggest sine can be of anything? What is the maximum? Like sine, think of angles. What is the maximum sine? When you take sine of an angle, what's sine of sine of 30 is 1/2. Sine of 45 is √2/2. Sine of 60 is √3/2. But the most sine can be is 1, right? That equals 1. So 1 or -1. So sine is either 1 plus or minus 1. That's the same thing with cosine. The biggest it can be is 1 or -1. So that's why when sine is 1, you're at the maximum right here. This is for sine equals 1. And that's why you put a 1 into place for all of this stuff here, and you get you would get negative 1.4 pi, okay, which puts you down here, and then you put -1 in for sine, and you get 1.4 pi, because 1 is the most it can be. That same holds true for cosine. The most cosine can be is 1. If you're on your calculator and you punch in sine of 30 degrees, you get some number above 1. That means you're in well, that means you messed up. That means you're in radians, probably. So degrees, though, I mean, the best it can do is 1 sine of anything. The best you can do is 1. Because sine's a ratio, right? It's a ratio of hypotenuse, of like opposite side over hypotenuse. Well, if in a triangle, you can't have, the opposite side cannot be, oh, there's what I was looking for. Oh, well. You can't have the opposite side bigger than the hypotenuse, right? There's the hypotenuse, there's the opposite side. So SOHCAHTOA, okay. Here's what I did this morning that actually was pretty good. I looked at this same sine cosine thing, and we looked at different points along the path of the pendulum going back and forth. That middle point is equilibrium. And we compared at each point, we compared what is the position, what is the velocity, and what is the acceleration. And then talked about why it would be that way. Like when it's at equilibrium, the position is 0. That's ground state. That's sitting at back. That's like, ground state for a pendulum is this, just sitting there like that, not moving. And that's the point where the velocity is the greatest, either positive or negative, going this way or going that way. And then that's the same thing as acceleration being 0, because at that point, the pendulum's happy. There's no, at that point, the gravity is pulling down and the motion is perpendicular, so there is no force acting on it. At the other extreme, if I'm at a maximum, angle, that's where the position is at maximum. I mean, this is going to pay off rewards for you. I know it's hard to get it all the first time, but the second time you see it, it'll pay off some rewards. The third time, fourth time. So here we're at maximum, either stretch if it's a spring, or maximum angle if it's a pendulum. At that point, there is no velocity, right? Because the thing's turning around. And at that point, like I said, at that point, you're getting the most bang for your buck out of gravity. It's pulling down the most. It's trying to get that object to move back and the further away from equilibrium you go, the more force gravity wants to get the pendulum to come back to its equilibrium position. So gravity is sometimes considered a restoring force. It's trying to get things back to lowest ground state. If I have an object on a table, gravity would love for that object. I mean, cats help the situation by knocking it off the table. But gravity's trying to get, I think cats are working in conjunction with gravity. Cats are trying to get, so the gravity's trying to get that object down to the ground, down to its ground state. All right. And that's true not just in gravity, but in potential, electric potential, ground state, yeah, springs, mechanics, engines, all the same thing. Okay, y'all, I have I've given myself a headache, so I'm hoping I gave you a headache. That means you were with me there for a while. You don't learn physics in one day or 1 year. Okay, just keep after it. And in about 4 or 5 years, you go, no, yeah, that's cool. But you're doing the right thing. Keep asking questions. Okay, so we're done. I'm going to stop recording now. Rose, you said you wanted to ask a question or two, so I'm going to not end it, but I'm going to stop recording. Hold on. Pause.